For every 33 feet a submarine sinks, the ocean adds another full atmosphere of crushing pressure onto its hull. By 1,000 feet down, that's 30 atmospheres squeezing in from every direction, enough to crumple solid steel like a soda can. And right now, somewhere in the Pacific or the Atlantic, more than 100 people are living inside a submerged steel tube well past that depth, cooking dinner, doing laundry, sleeping in bunks, with the ocean trying to kill every one of them every second. It shouldn't be possible, and the reason it is has almost nothing to do with how thick the metal is. In the next few minutes, we're going inside the actual engineering of a submarine, how it decides to sink, float, or hover in place on command, how its hull survives pressure that would flatten a tank, how a crew breathes air that's never touched the surface for 3 straight months, and how a 9,000-ton submarine becomes functionally invisible. And at the end, I'll show you a trick real submariners use, using nothing but your own lungs, that lets you feel exactly how a submarine like that controls its depth the next time you're in a pool. None of this is guesswork. Naval engineers calculate a submarine's limits using a fixed law of hydrostatic pressure, then physically prove it during real dives called test depth trials, before a single sailor is ever trusted aboard. The ocean doesn't negotiate, so neither does the engineering. So what actually decides whether a submarine sinks, floats, or just hangs there in the water? And what happens when that system fails? On May 23, 1939, the USS Squalus was running a routine test dive off the coast of New Hampshire when a critical valve failed and seawater poured into the engine room. The aft section flooded almost instantly, and 26 men there were lost. But in the forward compartments, 32 sailors and 1 civilian engineer were still alive, sealed inside a steel hull resting on the seafloor, 240 feet down, deeper than any trapped submarine crew had ever been pulled out alive before. Here's what matters. The Squalus didn't sink because the ocean crushed it. It sank because water reached a space that was supposed to stay dry. That's exactly what every submarine does on purpose, using ballast tanks. To dive, vents open and seawater floods in, pushing the air out until the sub is denser than the ocean around it and sinks. To surface, compressed air blasts back in and shoves the water out until it's light enough to float. And to just hover, the crew balances air and water in smaller trim tanks until the sub weighs exactly what the water around it weighs. It isn't fighting gravity, it's negotiating with it. That day, a brand new device called the McCann Rescue Chamber sealed over the Squalus's hatch and pulled all 33 survivors out alive across 4 separate trips. The first successful deep submarine rescue in history. But it only worked because 240 feet was well within that hull's pressure limits. Push past those limits and no chamber on Earth saves you. Because the danger stops being water getting in. It becomes the hull caving in. So if flooding isn't usually what makes deep water so dangerous, what is? Try this at home. Squeeze a raw egg end to end, hard in your palm. It won't crack. The curved shell spreads the force evenly across the whole surface with no single weak point. Now, squeeze a flat cracker the same way. It shatters instantly. Submarine engineers are betting a crew's life on the egg. A pressure hull is built as a cylinder for exactly that reason. The curve spreads the ocean's crushing force evenly around the tube instead of letting it collapse one flat panel at a time. It's welded from high-strength steel or titanium, designed to flex without cracking and pressure tested before anyone steps aboard. Engineers even build in a safety cushion on purpose. The U.S. Navy sets a submarine's official test depth, the deepest it's rated to operate, at only about 2/3 of the depth it's actually calculated to survive.
That gap between as deep as we need to go and as deep as physics allows isn't an accident. Submarines spend their entire careers nowhere near that second number. So, the hull can survive the pressure. Fine, but that means nothing if the crew inside it suffocates. And for a sub that stays under for months without surfacing, that's not a small problem. It's the whole game. So how does a crew of over 100 people breathe for 3 straight months without ever coming up for air? In 1954, the USS Nautilus became the first nuclear-powered submarine in history, and it broke every previous rule about how long a sub could stay under. Before Nautilus, submarines had to surface constantly to run diesel engines and refill their air. After Nautilus, the only thing that could force a submarine home was running out of groceries. Crews on modern nuclear submarines still describe it. Before a 90-day patrol, the whole ship gets packed floor to ceiling with canned food. Sailors line the corridors with cases of supplies, lay plywood over the top, and walk on their own pantry for weeks. And as the food gets eaten, the floor of the ship, quite literally, gets lower. Food is the easy part to plan for. Air seems impossible until you remember the submarine is floating in an unlimited supply of its raw ingredient. Water is 2 parts hydrogen, 1 part oxygen. So the crew desalinates seawater, then runs electricity from the reactor through it in a process called electrolysis, splitting the molecule apart. The oxygen gets pumped into the air the crew breathes. The hydrogen gets vented overboard. Meanwhile, the carbon dioxide the crew exhales gets pulled out of the air by chemical scrubbers and pumped outside. The submarine isn't carrying its air supply. It's manufacturing it continuously from the same ocean that's trying to crush it. Which means a nuclear submarine can, in theory, stay under almost indefinitely. It makes its own air, its own water, and it never needs refueling. The only thing standing between a submarine and total invisibility is whether anyone can hear it coming. Last question. How does a submarine longer than a football field just disappear? In World War II, German engineers gave this exact problem a code name, Albrecht, after an invisible dwarf from Norse mythology. They started gluing rubber tiles filled with thousands of tiny air pockets onto U-boat hulls. Enemy sonar pulses hit the tiles, scattered into the air pockets, and never bounced back clean enough to reveal what was underneath. Modern navies use the same trick today, just with better materials. There's no light in the deep ocean, so seeing a submarine really means hearing it. Active sonar blasts a sound pulse and listens for the echo. Effective, but it also announces exactly where you are. So submarines mostly rely on passive sonar instead, banks of underwater microphones that just listen and give away nothing. Everything else about the design supports staying silent. A smooth, teardrop-shaped hull cuts through water without the turbulence that creates noise. Rubber anechoic tiles soak up outgoing sound and incoming sonar pings. And machinery sits on rubber mounts, so a running pump doesn't hum straight into the ocean. When it matters most, the crew goes into what's called silent running. Non-essential systems off, movement minimized, speaking only when necessary. A submarine's best weapon was never really the torpedo. It's silence. And that's the moment this stops being an engineering story and becomes something a lot more uncomfortable. Because the same technology built to keep a crew of 150 people alive and hidden is also the reason submarines are considered some of the most dangerous weapons a country can own. Not every submarine is built to hunt other ships. Some exist for one purpose only: to disappear into the ocean, carrying enough firepower to end a war and to stay lost, sometimes for months, so that no first strike could ever take them all out at once.
They're called ballistic missile submarines, and their entire mission rests on one idea. As long as even one of them is out there somewhere in an ocean covering more than 139 million square miles, a country can absorb a devastating attack and still respond. Military strategists call this second strike capability, and it's considered the most survivable leg of a nation's nuclear arsenal, more survivable than missile silos, which show up on satellite photos, or bombers, which can be shot out of the sky. By some estimates, roughly 70% of all deployed U.S. nuclear warheads sit on submarines, just like the ones we've spent this entire video explaining. Quietly patrolling, engines dampened, waiting for orders their crews hope they never receive. Here's the uncomfortable part. Every piece of engineering we just walked through exists, in this case, in service of a machine whose entire job is to stay untraceable while carrying the most destructive weapons humans have ever built. The same silence that saved 33 men off the coast of New Hampshire in 1939 is the silence that makes a modern missile submarine almost impossible to find. It's not a flaw in the design. It's the entire point. So here's the one thing to take from all of this. The exact same principle that lets a 9,000-ton submarine hover motionless in open ocean is something you already control with your own body. Next time you're in a pool, take a normal breath and go still. You'll float. Now exhale most of that air and stay still again. You'll start to sink. That's the entire trick behind ballast tanks, scaled up about 1 million times. Your lungs are your own personal ballast tank. Try it tonight, and you'll understand submarine buoyancy better than most people who've never set foot on one. But here's what should actually bother you. If a submarine is engineered this well to disappear, no light, no sound, self-made air and water, hidden somewhere in an ocean covering more than 2/3 of the planet, how does anyone ever find one that doesn't want to be found? That hunt has its own insane engineering story, and it's happening in the ocean right now. Click the video right here to see how militaries actually track something built to be untraceable